I was sitting in a coffee shop this morning, just listening to the background noise, not really eavesdropping, just the hum.
Mm-hmm.
And I had this really weird thought. Physically, the human mouth is just meat. It's a tongue, some cartilage, a jaw, wet muscle.
Right.
And theoretically, the sounds that come out of us should just be total chaos. Squawks, grunts, whistles.
It should be acoustic anarchy.
Yeah.
If you just look at the biology, there's absolutely no reason we shouldn't sound like a barnyard.
Exactly. But we don't.
Yeah.
We aren't just making noise. We're like executing code. A really specific, incredibly rigid code.
We are.
So today, we're going to look under the hood of that code. We are doing a deep dive into Principles and Computational Models of Phonology by Stephen Bird and Jeffrey Hines. Specifically, we're breaking down how the brain and now our computer structure sound.
It's a fantastic choice because phonology is this perfect bridge between, biology, psychology, and computer science. We think of speech as just saying words, but phonology is the study of the hidden operating system that restricts that chaos you mentioned.
The OS of the mouth.
It's the set of rules that transforms a mental idea into a physical vibration in the air.
And I want to flag something for you listening right now. If you hear phonology and have, flashbacks to grammar drills, don't worry.
Oh, yeah. No diagramming sentences here.
This is not about where to put a comma or who versus whom. This is about the mechanics of your own mind. We're going to cover everything from why you hallucinate sounds that aren't there to how African tone languages act like musical scores.
And finally, how we're teaching robots to replicate this entire system. It is basically the source code of the human species.
I love that.
And the first lesson is that your ears are lying to you.
Okay, let's start there. The authors talk about this illusion of continuity. The idea that what we hear isn't necessarily what was actually said.
Right. This is the fundamental distinction between a phone and a foam. A phone is the physical reality, a measurable vibration in the air. If I hook you up to an oscilloscope and you speak, what it draws is the phone.
The raw data.
The raw data. A phone, though, is a mental folder. It's a category your brain uses to sort that reality.
Okay, walk me through this.
Yeah.
Because to me, if I hear a sound, I hear the sound. I don't feel like I'm filing it away.
You think you hear the sound, but let's run a quick test. Let's take the English letter T.
Okay.
If I ask you to say the word 10, do it right now and just put your hand in front of your mouth.
All right, hand is up.
Yeah.
10.
Feel that.
Yeah, a little puff of air, like a little explosion.
That's called aspiration. That puff is a physical thing. Now, keep your hand there and say the word net.
Net.
Get the puff.
No, nothing. My tongue just,
Rah.
it hit the roof of my mouth and stopped. Just cut the sound off cold.
Exactly. That is an unreleased T. Now, one more. Say water. Just the normal, casual way you'd say it.
Water. It sounds soft.
Yeah.
Almost like a really fast D sound.
Linguists call that a flap. So physically, we have three completely different acoustic events here. A puff of air, a hard stop, and a quick flap.
They sound different when you point it out.
They look totally different as sound waves. But if I asked a native English speaker, did I just use three different sounds? What do they say?
They'd say I used a T 3 times.
Precisely, because your brain files all of them under the abstract mental folder labeled T. In English, these variations are called allophones.
Go.
And the key here, and this is a term the authors use, is that they are in complementary distribution.
Meaning they don't, step on each other's toes.
Right. You never use the water flap at the start of 10, and you never use the hard stop in net at the start of a word.
It would sound weird.
It would. Because the difference doesn't change the meaning of the word in English, your brain just aggressively filters out the physical difference. It calls it irrelevant noise. It's pure efficiency.
Why store 3 sounds when one label works? That makes perfect sense.
It makes sense for English, but this is where it gets so tricky. That efficiency is specific to our code. If you go to Icelandic or Bengali, that little puff of air, the aspiration, is contrastive.
Right.
Meaning if you say a word with the puff versus without the puff, you are saying a completely different word. It's not an accent. It's a different meaning.
So to an Icelandic speaker, those 2 T's sound as different as, a B and a K do to me.
Exactly. And this is why learning a new language is so incredibly hard. You aren't just learning new words. You have to retrain your brain to stop ignoring data it spent 30 years learning to filter out.
You have to hear the raw data again.
You have to.
The source material brings up the IPA, the International Phonetic Alphabet here. I always thought it was just for, opera singers.
Right.
But the authors treat it like a periodic table for sounds.
That's a perfect analogy. The IPA isn't just a list of weird symbols. It breaks every possible human sound down into its component parts. Distinctive features.
It's like binary code.
It is plus or minus this, plus or minus that.
Like, is the sound voiced or unvoiced?
Correct. Or is it nasal or not nasal? For example, take P, B, and M.
Okay.
They sound different to us, but in phonology, they form a natural class. They all share the feature plus labial. They're all made by smashing your lips together.
So my brain doesn't just store the sound B. It stores a bundle of features, plus voiced, plus labial, nasal.
Exactly. And this feature engineering is what lets us solve the really complex puzzles, because sometimes sounds start acting, well, weird. They change based on their neighbors.
Which brings us to generative phonology.
Yes.
This was the part of the reading that felt like a detective novel. We start looking at how sounds change when they interact, and the authors bring up this great puzzle using Russian data.
The Russian voicing assimilation problem. It's a classic.
So for you listening, here's the evidence. We have the Russian word for bread, just the word on its own. It's pronounced slep, ends in a P.
Right. A P sound.
But if you want to say to bread, the dative case, it becomes gugable. The P flips into a B.
And we see this pattern again. The word for coffin is grop, but to coffin is grobu. Again, P becomes B.
And physically, a B is just a voiced version of P, right?
Yeah.
Your vocal cords vibrate for B, but not for P.
Correct. Same mouth shape, you just add vibration.
Okay, so looking at that, my first guess, my hypothesis would be when a voiceless consonant is next to a vowel, which is voiced, it sort of catches the vibe.
Peer pressure.
Yeah, peer pressure. It becomes voiced too.
That is a very logical, very surface level hypothesis. It's called assimilation. It happens all the time in languages, but then the authors throw in the twist.
The counter evidence. The word for corpse in Russian.
Right.
If you add the same U suffix to make it to corpse, it becomes trubu. The P stays a P. It doesn't turn into a B.
And just like that, your rule is broken.
It's shattered.
Because if it was just peer pressure from the vowel, trupu should have become trubu.
Right.
But it didn't, so why?
This is the aha moment in the text. The solution isn't about what's happening on the surface. It's about what's happening deep down in the mental dictionary.
Yes. The concept of underlying forms.
Abstractness.
A core tenet of generative phonology. The idea is that the word for bread and the word for corpse look similar when you say them. They both end in a P sound, but they are stored differently in your brain.
So the analysis is that the underlying form for bread is actually sleb, ending in a B.
It was a B all along, and the word for pond, which is pronounced prut, is underlyingly prude with a D.
Wait, but
yeah.
If bread is really sleb in the brain, why on earth do they say sleb? Why lie about it?
Because of a final devoicing rule. Russian has a strict constraint. You cannot have a voiced consonant at the very end of a word.
It's illegal in their code.
Totally illegal. So if the underlying form ends in a B, the grammar forces it to unvoice to sound like a P, but only when it's at the very end of the word.
But when you add the suffix...
The B is no longer at the end of the word. It's in the middle now. It's protected by that vowel. So the rule doesn't apply, and the original true underlying D gets to come out and play. Exabu.
That is just wild. So trup, corpse, stays trubu because it was always a P to begin with.
Yep. No secrets there.
But slep changes because it was secretly a B in disguise.
Precisely. It's called a neutralization rule. On the surface, slep and trup look identical at the end. But underneath, in the code, they're distinct. What we say is often a simplified, compressed version of what we store.
It's like file compression. We store the high-res file, but we transmit a JPEG because it's easier.
That is a great way to put it. But this whole idea of rules input, process, output leads us to a problem. Traditional rules assume language is linear.
Beads on a string. A changes B, B changes C.
Right, but the reading says language is actually 3D.
This is the shift to nonlinear or autosegmental phonology.
Oh, exactly.
And the authors use Turkish as the first example of this. Vowel harmony.
Turkish is fascinating. In Turkish, suffixes aren't static. They change their vowels to match the flavor of the root word.
Okay, what do you mean by flavor?
Well, if the root word has a back vowel, the suffix gets a back vowel. If the root is rounded, made with your lips puckered, the suffix vowel also gets rounded.
So it's like color coordination. If the main word is wearing blue, the suffix has to put on a blue hat.
That's a great way to think about it. But think about what that means computationally. The feature, say, plus round, isn't just stuck inside one letter. It's behaving like a blanket that's covering the whole word.
A blanket?
Yeah, phonologists literally stopped drawing sounds as a single line and started drawing association lines. Imagine the feature plus round is just floating above the word on a separate tier.
A separate track.
And it's sharing its property with all the vowels below it. It's a prosody.
And this floating idea becomes absolutely crucial when we look at tone languages. The source material breaks down a language called Chakosi from Ghana. This part, it blew my mind. I've never thought of pitch as a physical object before.
Tone languages are notoriously difficult for linear theories. In Chakosi, the pitch of your voice changes the meaning of the word. But if you just look at the data for the word bulali, which means iron.
It seems chaotic.
Totally. Sometimes it's low, high, low. Sometimes it's high, high, high. It looks random.
If you were just looking at the letters, you'd never find the pattern.
But if you separate the tones from the letters, if you treat the melody as a separate layer from the lyrics, it makes perfect sense.
They describe this mechanism called high tone spread.
Right. So imagine a high tone is strong. It wants to spread to the right. In Chakosi, if you have a high tone followed by a low tone on the next syllable, the high tone spreads over and basically kicks the low tone off its syllable.
So the low tone just disappears.
No, and this is the coolest part. It gets delinked. It becomes a floating tone.
A floating cone.
It has no syllable to attach to, no lyrics to sing, but it still exists in the math of the sentence. It's like a ghost.
A ghost tone.
Essentially. And this floating low tone causes a downstep. It acts like a little gravity well. It pulls the pitch of the next high tone down a little bit.
So you don't hear the low tone itself, but you hear its gravitational pull on the next word.
That's it.
That is unbelievably complex. It's like invisible dark matter in the sentence structure.
And native speakers are doing this math in milliseconds while they're, arguing about the price of fish.
It really highlights how the linear beads on a string model just falls apart.
It does.
You need that 3D architecture.
Yeah.
And speaking of architecture, we have to talk about the container these sounds sit in, the syllable.
Right. We take syllables for granted. We clap them out in kindergarten. But they are a fundamental unit of organization.
Remember our friend the English T?
Yeah.
The puffy one versus the stopped one?
Yeah. Why do we say cactus with that aspirated T, but atlas with a tight, unreleased T?
I always just assumed it was because L is hard to say after T.
But it's really about syllable structure. In cactus, the T starts the second syllable. Cactus. It's in the onset. In English, onsets get aspirated. But in Atlas, the T and L don't blend well together at the start of a syllable. You can't start an English word with TL.
Right, that sounds wrong.
So the T gets stuck at the end of the first syllable, the coda. And codas in English don't get aspirated.
So the T changes its close depending on which room of the syllable house it's standing in.
Exactly. And this becomes so obvious when languages borrow words. The source talks about the Jung language from Cameroon.
Right, they borrowed the English word mat. But Chang doesn't allow a T at the end of a syllable. It's illegal in their code.
So what do? They can't just leave it there.
They add a vowel. Mat becomes meta.
Right. By adding the A, the T is no longer at the end. It becomes the start of a new syllable.
They repair it.
It's a repair strategy. It preserves the consonant by building a new room for it. But sometimes they just nuke it. The English word det becomes de-eek. They just change the sound to a K because K is allowed in the coda.
The most mind-bending example of syllable logic for me was the Olwa language of Nicaragua.
Oh, the infix.
Yeah, to say my or your, they don't use a prefix or a suffix. They jam the sound inside the word.
But where? It's not after the third letter or anything simple like that.
Well, it's based on syllable weight.
It looks for the first heavy syllable. A heavy syllable usually has a long vowel or ends in a consonant.
And the grammar just weighs the syllables on a scale, finds the heavy one, and slices the word open right after it to insert the possessive.
It's just relentless logic.
It is. But, and this is where the reading takes a massive turn, eventually linguists realized that having thousands of these specific rules, insert A here, delete B there, was getting messy.
It was becoming a laundry list. Do this unless that, except on Tuesdays it wasn't elegant.
Not at all.
So in the 90s, the field shifted towards something called Optimality Theory.
This is the survival of the fittest segment.
Exactly. Instead of rigid rules that process an input, Optimality Theory suggests we have a set of universal constraints. But these constraints are always at war with each other.
And the two big fighters are markedness and faithfulness.
Right. Markedness is the force of laziness. It says, make things easy to say.
Okay.
It wants to get rid of hard sounds, voiced consonants at the ends of words, complex clusters. It wants everything to be simple, like ba ba ba. And faithfulness is the opposite. Faithfulness is the force of accuracy. It says, don't change anything. Pronounce the word exactly as it is stored in the dictionary. Don't delete sounds. Don't add vowels.
So they are fundamentally opposed. You
Yeah.
can't be lazy and accurate at the same time.
You can't. And the insight of optimality theory is that the only difference between languages is how they rank these constraints. Which one is more important?
Let's go back to Russian versus English.
Perfect example. Russian ranks the markedness constraint, no voiced sounds at the end, higher than faithfulness.
Okay.
So when the word is grob, often, markedness wins the fight, it forces the change to grob. Laziness, or let's say structural simplicity, beats accuracy.
But in English?
English ranks faithfulness higher. We say lab and lap differently. We preserve that voicing at the end, even though it's physically a bit harder to do.
So faithfulness beats markedness.
Yep. So it's not that Russian doesn't want to be faithful or English doesn't want to be simple. It's just about who wins the argument in that specific language's ranking.
The brain runs a simulation.
It's called a tableau. It generates a bunch of candidates for how to say a word, gra, bra, bra, grobu. Then it filters them through this ranked list of constraints until the least bad option is left standing.
The one with the fewest violations of the most important rules.
That's the winner.
Which brings us to the final frontier. If our brains are running these algorithms, can we teach a computer to do it?
This is computational phonology. We are trying to translate these linguistic theories into literal code. Python, C++A, you name it.
The authors mention finite-state transducers, or FSTs.
An FST is basically a machine that takes an input string, like the underlying form, and moves along it, step by step, spitting out an output string based on the rules.
So with the Russian example, it would read PRUD, hit the end of word signal, and the machine just clicks over and outputs a T.
Simple enough. FSTs are incredibly efficient. They are the workhorses of things like text-to-speech. But the reading highlights a big problem.
They're linear.
They're linear. They're great for beads on a string problems. But remember the African tone languages or Turkish vowel harmony?
The 3D stuff, the ghost tones.
Exactly. An FST is like reading a scroll through a straw. You can only see a little bit at a time. It struggles when information has to jump over 5 different letters to affect something down the line.
So how do they solve that?
Well, computational linguists use something called attribute value matrices, or AVMs.
The nested folders.
Right. Instead of a string of letters, the computer treats the word as a hierarchy of features. This allows for those shared structures. It can handle that multidimensional geometry we talked about.
But it's more complex.
Much more powerful, but computationally a lot heavier.
And the big question in the field right now seems to be, do we have to manually program every single one of these rules into Siri or Alexa? Because that sounds exhausting.
That's the formal approach. And yes, it is exhausting. The modern shift is toward empirical approaches. Machine learning.
Just feed it data.
A lot of data. You feed the computer millions of hours of audio, and you let it statistically figure out the patterns on its own.
It learns the ranking of the constraints by itself.
Ideally. Though the authors note that there's still a massive debate between the formalists who want to prove theorems about how language must work and the empiricists who just want a model that predicts the right data.
Even if we don't know how the machine got there.
Right. It's the difference between teaching a child the rules of chess versus just letting them watch a million games until they get it through osmosis.
What's a great comparison?
And we're finding that the pure statistical models sometimes hallucinate rules that don't exist, while the rule-based ones are too rigid to handle slang or new words. The future's probably a hybrid of the two.
So what does this all mean for the person listening to this right now? We've gone from puffs of air in 10 to ghost tones in Ghana to constraint battles in the brain.
It means that every time you open your mouth, you are performing a miracle of computation.
Wow.
You're taking a concept, retrieving an abstract code, the underlying form, running it through a gauntlet of conflicting constraints, managing syllable weights and tone spreads, and then sending motor commands to your lips and your tongue.
All in a fraction of a second.
All while you're thinking about what you want for dinner. It really highlights that language isn't something we do, it's something we are.
That is humbling. Before we go, I want to leave you with a thought from the very beginning of the reading that really stuck with me.
Okay.
The authors mentioned that speech is a motor activity involving the coordination of independent articulators.
Meaning it's physical movement. It's meat moving in space.
Right. And because it's physical, they say perfect repetition of any utterance is impossible. You never say the same word exactly the same way twice. The pitch, the speed, the exact milliliter of air, it's always different.
That's true. We are snowflakes of sound. No two hellos have ever been identical in the entire history of the species.
So, if that's true, is there really such a thing as standard pronunciation? Or is language just a collective hallucination where we all agree to pretend that these millions of unique, messy, physical sounds are actually the same few dozen neatly organized phones?
That is the ultimate question. The order is in the mind, not in the mouth.
Something to chew on next time you order a coffee. Thanks for diving deep with us.
My pleasure.
See you in the next one.